So in theory, this is live at this point. I'm just going to wait a couple more minutes while others gather. Again, this will be a presentation where I'm not getting live feedback. And this time I am doing it from my home office. It is, after all, coming up on the weekend, and I have some fun plans. And I hope to start those plans early. Oh, wait, one more minute here. All right, so here we go. This is a quick, probably a 20-minute presentation on some thoughts I had about problem solving in healthcare using technology. I'm going to talk about some of the projects I've undertaken and also some of the challenges and learning that's happened over the years as we've done this. There are a few takeaways that you will hopefully leave today with. First one is a little explanation of some stories. Stories of what didn't work, because those are the fun ones. Those are the ones where we all get to relate to one another and maybe commiserate on what it's like to be a human being. The second bit are a couple mental models that I've been playing around with to assist in decision making and evaluating approaches and figuring out risks in solving any problems. And usually we like to look at as many risks as we can and solve the big ones that will, when they're solved, contribute to a better probability of success, the outcome. The two mental models I'll describe is sort of an Occam's razor inverted. So it's evaluating the probabilities and dependencies to get a particular outcome. And the second mental model is the idea of looking at bottlenecks in a system, a problem with a set of sub-problems, see how those problems relate to one another and the likelihood of success, and identify, and I'll give you an example in the presentation about if you resolve one bottleneck, how other things will adjust in the system. I'll give that just in a toy example of Parkinson's dementia diagnostic algorithm, say based on EEG. And then lastly, I'll give some recommendations. And you can take those as you may, kind of in the context of your own projects and own problems, and see if they apply. So I've been doing tech development and signal processing, and creating algorithms for quite a while now. And one of the early projects out when I was in San Francisco was to modify computers by adding buttons and peripherals to make it easier for people with physical disabilities to use the technology. And that was a very introductory situation for me. I was a cog in the overall system of all of the problems in a startup organization, and I delivered what was needed, and the company succeeded. Not necessarily because of what I did, but because of how the company was situated and the principles of that organization and who they knew and were involved with. Sometime after that, I had this idea, okay, well, I'll run a startup and I'll create a product, which is a web-based EEG portal that could be used to for people to upload data, EEG data, run a set of algorithms, and some kind of diagnostic information would be sent back to the person or organization that uploaded the data. So I prototyped something for Alzheimer's disease risk marker detection from EEG data. And so I took an algorithm that was developed elsewhere, stuck it on an online portal, and yay, sort of demonstrated it could work. So technical feasibility of it. In that particular case, I really didn't investigate the business problem at all, how the economics would work or the ecosystem in which this would work. It was simply in my mind just to demonstrate the concept. After that, I built an online portal for medical persons, to upload EEG data and have them cleaned to make the data more usable. And the technology development around that was ways of removing artifact from various types of data, specifically EEG data was the target. And it was quite useful for the quantitative EEG world for various reasons. Yet it wasn't readily adopted. And primarily the reason for that is I was not involved with those persons who essentially controlled the market. So there was some learning there. Slowly, you may see a trend as I'm learning less in my evolution here, that less about the tech, it's more about the problem ecosystem. So at some point, I became involved with another organization, and we built some EEG-based technology. And this is where I learned more about technology translation, taking things that work in the university, and essentially the job being to make it work in the real world, for it to be robust, for the technology, the algorithms, the hardware, the sensors, all of that to work well together to get appropriate diagnostics performance, to explain outliers and false positives and do all of those sorts of things. And be sneaky and innovative in a way to develop IP and get it all to work. So again, very technology focused. And it works great. The downside is that it essentially didn't get adopted. And the likely reason is that simply the users of this technology are just very, very busy. And this is the revelation for me is people in the healthcare, nurses, doctors, and whatnot are just busy, too busy, overworked, and it's very, very hard to take on new tasks. And so this is what I did. This is what my colleagues and I did. We gave doctors and nurses another box to use that requires they put more sensors on a patient, that they manually record data. The situation required that there be some cheerleading for those using the technology to take measurements from the patient. And we created some incentive dashboards so that they could see the impact. So they could see the impact of their extra work. And some reflection on this, I alluded to this earlier, is so where does the greatest risk in bringing medtech to market actually reside? Is it in the technology itself? Is it in the university translation of experiments into the real world? Or is it more about the ecosystem adoption of the technology? Who has time to use it? And this is something that's about me. And this is very much about my personal values and what I see as possible in the world. But let's use this as an example for our talk today. I want to make a box that assists neuropsychiatrists and patients in their brain health assessment, patient brain health assessment. and a box that does some early screening for various types of mental health issues and neurodegenerative diseases. And this box could predict health trajectory for each person, and it could plot those persons with respect to other people, groups in the population, and we can visualize our own projected health outcomes. And I want these, what I think are technologically achievable things, to be available to everybody. And so more reflection. Are these good ideas? Is this a good idea? And generally, those black boxes seem like good ideas. I don't think they can become generally available until we make some big changes about how we innovate in medtech. I think the biggest challenge is about choosing what to do first. And well, what can be guessed is possibly the biggest barrier faced in healthcare and hospitals. Let's just, for this talk, assume that this is correct. Let's say it's time. Let's say it's nurse time, doctor time, patient time. And then maybe the second ranked item after time could be mental load, doing multiple tasks, having to prioritize things, having things essentially drop off the list. What I'd really like to do is tell nurses and doctors, medical professionals who work in hospitals and clinics, that I'm not going to make them work harder. I'm going to tell them I'll put a little device inside the box they already use, but they don't have to change anything they do, and there are no new tasks, and that in a year's time, they'll have 2 extra free hours a day, because what we're doing inside of that black box, that they already use, we've collected some information, we've had some innovation, patient insights, and can provide these diagnostic capabilities I talked about. I want to be able to tell patients, given what I've learned, I want to tell them they'll be assessed in many ways automatically. They don't have to commit extra time. There's only one place they have to go. And their own work and their strife around their health can be reduced. That their current status can be identified, and estimates of their prognosis given with treatment options. And in 2 years' time, they'll be able to spend less time moving between appointments and getting readmitted to hospitals and experience fewer missed symptoms. Now, this 2 years' time bit that I'm adding on here, I'm just picking a number out of the air and saying, okay, well, I'm going to develop something that's going to do this thing. That's a time saver for patients and medical professionals. It's going to take 2 years to develop, and then we're going to deliver that, and it's going to save people time. Again, reiterating some lessons learned here is there has to be someone to use whatever box we create. There usually isn't anyone available, and generally speaking, people are overworked. So digesting that, let's switch into a mental model mode here, and the two that I suggest I'll talk about. One is about probabilities, and in a bit in the context of Occam's razor. And so you probably have come across Occam's razor. Generally said, if you have 2 competing ideas to explain something, you should prefer the simpler one. And for myself, I always just assumed, okay, it is what it is. I never ever thought more deeply about what they actually mean. There's another way of saying this, is the more things that need to be true together, that are independent of one another, the less likely the outcome will occur. And I can represent this in the next slide as for to have the outcome Z, A has to be true and B has to be true. Occam's razor might even go even more simple, which is, okay, only A has to be true, and it isn't dependent on B also being true. Again, the fewer things that need to be true means the less complicated the outcome is. So if we make this more complicated, we could say A And B and C and D and E have to be true to have an outcome Z. So let's put this in the context of a toy example where we're going to create some marker, Parkinson's dementia marker. Let's say we're going to use do university translation from EEG technology from somewhere. And it's about making the algorithms more robust, about having some kind of thing to collect data and sensors and some kind of business model, blah, blah, blah around it, and someone to use it. So let's start simple. Let's say it's just the top half of the slide here. The tech has to be made robust enough to work in real world environments, and a nurse has to have time. And the result being there's general use of this in this technology in hospitals. Let's add some more detail to that. The technology has to be robust. It has to have some FDA or CE approval. It has to have some kind of accuracy. There has to be maybe some billing code associated with it, and the nurse has to have time. And if all those are true, then it can have general use in hospitals. Now let's take it a step further and assign probabilities to this. These are probability between 0 and 1. As someone who has done technology translation for EEG algorithms in the past, I can throw these numbers in here, but they're relatively educated numbers. And they might even be higher than this. But let's just be conservative and say there's a 0.8, a 0.8, a 0.8 in each of these, right? So 80% chance that the technology will be robust enough, 80% chance of CE and FDA approval, 80% chance that it's going to be accurate enough, and 80% chance that there are billing codes and everything will work together, and there'll be some kind of financial model associated with it. I'm using billing codes as a simple financial model. But what we know to be true is that nurses are busy. Clinicians are busy in the hospital environment in Canada, and I understand in all of North America. And so we put a 0.1 there. Right? And it turns out with independent probabilities, we can do this in a really simple way. With independent probabilities, we multiply them to get the resulting probability. And so in this case, there's a 0.04% chance that we'll get the outcome we want. So that question comes up is, okay, we're doing technology translation and bringing something to the real world. Off the cuff, I can come up with these 80% probabilities and the 0.1, which is really the huge barrier here. And so that question comes up is, where should a company spend their time? For myself, I buy into the philosophy of addressing the biggest risk first. So let's go back to reflection mode for a moment. And from this example, is if the nurse has 10% probability of them having time and that being true, how do we up this to 80%? And if I put on my product owner hat, product developer hat, and my scientist hat, I think I could say, okay, let's try considering example 1, which is to simulate and demonstrate the proposed device takes no additional nurse time. Wouldn't that be amazing? Well, what about option 2 here, which is, well, let's simulate and demonstrate data collection to create and train a device that takes no nurse time. And once that device is built, right, after this 2-year mark, we'll simulate and demonstrate the time savings that'll occur when this is completed, when the device is being used. And that could be, the time saving could be not direct to that specific nurse, but it could be in patient readmission. It could be the time to provide diagnostics and get a result, a correct diagnosis, in this case, Parkinson's disease, come in many ways. And then more reflection, that question comes to mind for myself is, are we still a tech company when we're now doing simulations of the technology in terms of developing the technology in the ecosystem. And then when it's implemented in the ecosystem, doing simulations. So are we a company that now designs systems and process healthcare and specializes in understanding the dependencies of all things? So let's choose a little bit of column B there and say that we're a company that where our one of our key strengths is understanding the ecosystem of healthcare systems and how to move things around the bottleneck, right? In our first example, the bottleneck was nurse time, clearly, right? It had that 0.1 or 10% probability that a nurse has time. So this new slide here, the top just illustrates what we've seen already. The bottom is if we say, okay, we're not going to build new electronics for our offering. We're not going to create new sensors for our offering. And in fact, we're not going to try and train people to use it, at least not the nurses who are not familiar with using EEG systems and electrodiagnostic. What we'll do is we'll build a set of algorithms, and we're going to get people in the existing electrodiagnostics department to use it because they're already putting on EEG sensors. They're already using EEG hardware for other purposes, and perhaps, this is again an imaginary example, perhaps they have the expertise already to do these, collect good data, et cetera, et cetera. And let's assume we do this. Now we no longer have to be concerned about whether or not the electronics are going to work, that we're going to get clean signals, that there are not going to be noise contaminations, that the sensors are going to be okay, because we're using existing hardware and sensor technology. So now we get to focus on algorithms. We've strategically, through understanding our ecosystem, identified a path that relies less on the patient care and nursing and relies heavily on electrodiagnostic technicians. So this is about moving the bottleneck. And just in our toy example here, I put some numbers in there. In this case, a little bit of time is spent with the patient care nurse, passing information back and forth. The bulk of it goes into the EDS technician time, and we remove the unknowns essentially for electronics and sensors, and we up our probability or chance of success. Now, again, these are toy numbers. The whole point to illustrate here is that we can get the probability to go up by looking at the ecosystem and figuring out what problem to solve first. Let's see here. Now, let's go to the next slide here. So, some recommendations, and this is based on my own experiences in journey and whatnot, is to do what can be done to simulate the ecosystem and simulate the adoption of the technology before spending money on the technology itself. To understand what we actually need to build and what the minimum thing to build is. And in this toy example, the minimum thing to build is algorithms. And the deliverable is sort of this time savings, right? The other recommendation thought is to do whatever we can, and this is a no-brainer really, is to design for the current workflow, and if possible, don't change the workflow. The downside, or rather the challenge, is when introducing a black box, another thing and another process, is the workflow does change. It adds complexity and it requires more time. Now, maybe an increase in, adding a black box, adding some complexity, maybe it's possible by doing that we can recuperate time, once we demonstrate it in the ecosystem. for a year, but that's a risk. And so how to mitigate that risk would be to simulate it. I don't mean necessarily specifically in a computer with probabilities and blah, 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 but certainly to try it, to put it in a department, to get people to use the thing, to do the stuff, and just simulate an outcome and see what happens. And I don't have any answers, about how exactly that will work, but I do know it's one of the major risks in the projects that I've been involved in, is simply adoption into the ecosystem. Something else that keeps coming up through interaction with other organizations and whatnot is often organizations want to build new hardware. And there's some need for that. And I don't fully understand it. There could be many, many things and reasons for doing that. Everything from, part of the IP process to belief that better hardware can be developed. But we're in this place where we've got all of these algorithms that are demonstrated in university as being feasible and possibly doing some really wonderful things to help us with patient diagnosis. Another project I was involved with is looking at schizophrenia. The analysis done there in California demonstrated that there might be 5 variants of that or more, and that it's feasible to figure out which variant a person potentially has. And so what's needed there is essentially algorithms, some kind of box that measures EEG data, and it does the things. So carrying forward, the big lesson here is don't give more work to nurses and doctors, and it's just focus on figuring out how to free up their time in the short term and in the long term. And if the short term we can't free up their time, or we have to give them extra work, if there's some way to prove in a simulation that extra work is guaranteed to reduce time, a year from now or 2 years from now, that probably go a long way. And that's all I got for today. If you have some comments, please drop them into the LinkedIn comment section or direct message me. I'd love to chat about this further because it's a big interest of mine. And it's an area I'd really like to understand more and offer more, if I may. Thank you.